In this video, we'll talk about classification in which the variable you want to predict is discrete valued. In this and the next few videos, we'll develop an algorithm called logistic regression, which is one of the most popular and most commonly used learning algorithms. And after these few videos, you'll be able to implement it and apply it to your own classification problems. Here are some examples of classification problems. In the email domain, if you want to look at a piece of email and classify it as either spam or non-spam, that's an example of a classification problem. Or if you run a website, an e-commerce website, and you want to look at the transaction and figure out if it is fraudulent, that's another example of a classification problem. Or in the medical domain, if you look at, say, a tumor and want to tell if it is malignant or benign, then that's another example of a classification problem. And in all of these, the variable that you're trying to predict, y, takes on one of two possible values, so it's discrete valued. And we usually use 0 and 1 to denote the two clauses. So for example, 0 may denote not spam or not fraudulent or not malignant, and 1 may denote a spam piece of email. For now, I'm going to develop classification in the case of when we have just two clauses, two discrete value clauses, and these ideas can be generalized later as well to problems with more discrete clauses. Just to give these two clauses a name, the clause that we assign a label of 0 to is often called the negative clause, and the clause that we label 1 to is often called the positive clause. And the terms negative and positive are somewhat arbitrary, and I wouldn't worry too much about them. You could just as easily have made spam the negative clause and not spam the positive clause, but this is just another way of referring to the two clauses. Let's look at an example of a classification problem. So this is an example that I had discussed a bit earlier, where you want to look at the features of a breast tumor, right, and tell if the tumor is malignant or benign. And so we have a variable y, which is either 1 or 0 to denote whether or not it is malignant, malignant meaning harmful, or benign meaning sort of relatively harmless. And on the horizontal axis with a feature x, which is the tumor size. So this is what a training set may look like, in which we have, say, a few negative examples, zeros, and a few positive examples. One natural question to ask is, well, why don't we just apply linear regression to this problem, right? And in fact, because we already know how to do linear regression, and in fact, if you apply linear regression to this data set, you fit a straight line like that, maybe. And what you can do is then threshold your classifier, right? So you have h of x of theta, which is theta transpose x. You can threshold at 0.5 so you predict 1 if h of x is greater than or equal to 0.5, and you predict 0 if h of x is less than 0.5, say. And it turns out that in this example that I drew, it'll actually work okay. This is 0.5 on the vertical axis, and so your threshold here, everything to the left you predict 0, everything to the right you predict 1. And that actually works pretty well. But it turns out this doesn't always work. And in particular, let me extend this axis and let me add just one extra training example out here, right? Or maybe I'll add a few training examples. If you do that, notice how the mapping from x to y, right, this horizontal x-axis, the mapping from x to y is still crystal clear. Right? Basically, everything to the left over here, right, is partly y equals 0, and everything to the right here is y equals 1. But by adding these extra training examples out here, if I run linear regression on this new data set, I would instead get a straight line fit to the data that maybe looks like that. Right? And if you continue the threshold at 0.5, the threshold is now around here, and so everything to the left of that you predict 0, and everything to the right of that you would predict 1. and this just looks wrong with a training set where it's as obvious as this what's going on. This is just right. This line. This is just not doesn't seem like a reasonable location to to place a decision boundary or to decide where to how to separate the positive and negative examples. So these new examples, they really didn't tell us anything new, and there should be no surprise to the learning algorithm that these are positive examples. But when we were using linear regression, these 3 examples out here dramatically changed the hypothesis to something that doesn't really make sense anymore. This example illustrates why it's often a bad idea to use linear regression for a classification problem. Sometimes you get lucky and it might work well, but it's not usually what I would do. Turns out that linear regression has one other strange property, which is that in a classification problem, we know y is either 0 or 1. But if you're applying linear regression, as you saw in the figure just now, we saw that h of x can be greater than 1, and h of x can be less than 0. And this also seems a little bit strange when you know that y is either 0 or 1. So when we develop the logistic regression algorithm, we'll see that one of the properties of the algorithm as well will be that the logistic regression algorithm will output values only between 0 and 1, and it also will not suffer from the problem we saw on the previous slide, in which adding a few more examples to the far right side ended up with a poor fit to the data.